The sun has the biggest magnetic field in the solar system, and the sun is basically a gigantic ball of plasma, so it doesn't have to all flow or rotate at the same rate. The equator of the sun rotates faster. The equator takes about 25 days to go around once, whereas the poles, it's a little bit slower at 30 days to go around once. So let's start off with a plain magnetic field similar to like what the Earth has, where you have magnetic field lines coming in from the south, goes up through the object, planet or star, comes out through the north. So then you have a south pole and a north pole, and then it would loop around and come back. All right, so that's a simple magnetic field, like a bar magnet. Let's start off simple, and then let's let the equator rotate faster. So the equator will rotate faster, and it'll drag those magnetic field lines with them. So moving charges can make a magnetic field, but when those charges move, they can also drag the magnetic field. So since the sun is a giant ball of plasma, when the gas rotates, it holds onto the magnetic field and drags it with it. So the rotating sun is dragging the magnetic field and is going to wind it up. And that's this last part here. Imagine taking a rubber band and winding it up and winding it up and winding it up, and eventually it's not going to have just a nice helical structure to the wind. It's going to start getting little kinks in it, little knots that'll pop out from the stress. And so that's this right here. You get these little knots that pop up due to the stress of the magnetic field. It just wound up too tightly. Here is the same thing in video form, in case that helps. So we're going to start off with the sun, having just a regular magnetic field, north pole to south pole. Let the sun drag it around. And eventually there's so much pressure in all those magnetic fields that it starts to get twisted and some knots pop out of the sun. Eventually there's so much pressure, all of those knots will snap and the sun resets back to a nice north pole, south pole structure. So we're going to end up actually with a cycle. Nice magnetic field twisting up, lots of knots, and then it snaps and resets and ends up again with a nice magnetic field and does the whole process again. One fun fact is that every time the magnetic field resets, the north pole and the south pole flip. So during the first part of the cycle, the north pole of the sun might be facing up, but during the next part of the cycle, the north pole of the sun is actually facing down. Right. So those knots of magnetic field that pop out of the surface of the sun when there's a lot of pressure are visible in the ultraviolet or the X-rays. So here's a picture of one of them. That's a magnetic field that pops out of the surface of the sun, and the magnetic field can trap hot ionized gas in it, so it can trap the plasma. And so the hot plasma gets trapped in this arch, and you can see that in the ultraviolet usually. And we call that a prominence. So here is a prominence. It's a visible, because there's hot gas trapped in it, a visible magnetic field of the sun. Okay. When you have this happening, the magnetic field is punching into the surface of the sun right here at the base and right here at the base. In this diagram, it's right here and right here where the plasma is punched through by that magnetic field. And you follow the magnetic field further into the sun, and what this means right here is the magnetic field, when it punches through the sun like that, stops the convection. So the magnetic fields pinch the surface of the sun, hold that gas there, let it cool off without letting any hot gas back in. So that's why sunspots appear. Cooler regions of the surface. Cooler regions of the surface because that magnetic field doesn't allow convection. Sunspots are not black. They're hot enough to glow red. But if you're looking at the sun safely and you see the bulk of the sun, the photosphere, and it's bright, your eye will see the sunspot as black just because it's dimmer than the rest of the photosphere. So sunspots are actually red just because they're a little bit cooler. So sunspots happen at the base of prominences. Here's some more pictures of prominences. Here's the sun. Here's a prominence. Earth photoshopped in for comparison. The sun's weather dwarfs us. Here's a little video of one. So this was taken with a space telescope, and while this prominence is happening, and there's probably other prominences on the sun as well, you're going to get extra particles escaping from the sun. And when a particle from the sun slams into your space telescope, it leaves little white pixels on it because it puts too much energy into that pixel right where it hits. So that's all these little white pixels that show up here, is the space telescope is getting bombarded with particles. Solar prominences can last days or weeks, but eventually they will fade away, kind of like a hurricane on Earth. It'll just eventually fade away. Here's a gorgeous picture, literally, truly an actual picture of the sun, but definitely it has been enhanced. But hopefully you can find the prominence. Here's the main prominence, stretching up and out and over and then coming back. There's some little ones in here. Little prominence, little prominence. Right. If you were to look at this in the visible light, you'd see a dark spot right here, and definitely over here, a dark spot. Sunspots, we've already talked about what causes them. That's where the magnetic field punches through the surface and stops convection. The surface cools to 7,000 degrees Fahrenheit roughly. That's down from 10,000. The photosphere is around 10,000 Fahrenheit. So in these places it's quite a bit cooler. Here's a little video of watching the sunspots turning with the sun. And watching the sunspots rotate around with the sun was the first way we could actually figure out that the sun does rotate and how long it takes to go around once. 25 days at the equator, 30 days at the pole. This sunspot, zooming in on it, is about the size of Earth. These bright and dark regions over here, that's just the regular pattern from the convection. There's hot gas rising up in the bright spots and cooler gas getting ready to sink in the dimmer spots. But this extra, let's call it feathering, around the sunspot is just the magnetic field starting to affect the convection around there. So if you were to zoom in on that, it is pretty. It's gorgeous. And remember that one of these little white spots right here is roughly 600 miles across. So I told you that the magnetic field winds up and then it snaps and resets, and that way we're going to end up with a cycle. So if you were looking at the corona, so this picture over here is we're looking at the corona for one full cycle of the sun. The corona is actually very quiet. There's not a lot of X-rays coming from the sun. It's very smooth. Right. But then as the magnetic field winds up, the corona becomes more active. And this would be called solar maximum, when the sun is the most active. This would be called solar minimum right after it resets. And it's roughly 11 years between maximums. So the cycle takes about 11 years. You know, sometimes it's 12, sometimes it's 11, but roughly 11 years. The last maximum happened around 2014. So we've got a while yet before another solar maximum. While the sun is at solar maximum, you're more likely to have a solar flare. And a solar flare is basically when a prominence snaps open. There was too much pressure in that magnetic field line, and it snaps open and releases a lot of gas and particles and energy to space. Boom. And then you notice the camera and a little bit later gets pelted by particles. There's the flare, there's the particles hitting the camera. You could call a solar flare the biggest explosion in the solar system. If you were going to compare it to explosions on Earth, we'd say it's billions of megatons and up to 100 times more X-rays and particles than the sun would normally give off if there was not a solar flare. What we need to be careful with on solar flares is those particles can affect our space satellites and can overload the circuitries, or it can induce extra current in our power grids on Earth. So we need to be aware of them and possibly power down our satellites or power down our grids if a solar flare is heading towards us. Our sun is awesome. Okay. I would also like to show you this animation. A solar flare, which is basically a big explosion, big release of energy, also sends out a shock wave across the surface of the sun. And if you think of the sun as like a liquid, it sends a wave out like a tsunami. And I briefly mentioned this earlier, where if you watch the speed of the waves across the surface of the sun and also how fast they go through the sun, you can learn a lot about the temperature and the structure of the sun. But here's an actual image of it happening and traveling out across the sun. With coronal mass ejections, or CMEs, it's when a large amount of mass is blown off of the sun during a solar flare, and these particles explode away from the sun at nearly the speed of light. Here, I'll play it again. And eventually you can see the particles hitting the camera, making those white pixels. In case you're wondering, this little white circle is the photosphere of the sun. It indicates the size of the sun. But since we're trying to watch the corona, we've blocked it out. And we've blocked out quite a bit more too with this disc. So that's blocking out our view of the sun. And something had to hold that disc up in front of the camera. So there's a bar right here holding up the disc. I happen to like it when these are launched towards the Earth because we'll get aurora. These particles are the ones that'll get directed by our magnetic field down by the North Pole and the South Pole, and they'll make aurora when the particles slam into the atmosphere. But power companies need to be aware of this because they have caused blackouts. It can overload the currents in the power grid. So you might want to power down a little bit if you knew one of these were coming at you. And you could also power down your space satellites so that they don't get overloaded when a huge amount of charged particles were to hit your circuitry. So on Earth we're pretty protected, but we still keep track of them. So this is a video of a coronal mass ejection launching off. Plenty of those particles made escape speed, but some of them rained back down. And so I thought this was an interesting video to show you. Particles launch up. And some of them rain back down a bit later.